Let's begin with some easy ones. So we start with having a equals b. So this means if we multiply the both sides by a, it will be a squared equals ab. That would imply a squared minus b squared equals ab minus b squared. So that means a plus b, a minus b equals b times a minus b. And now we can divide the both sides by a minus b, so that means a plus b equals b. So since a equals b, we substitute that. That gets b plus b equals b, which means 2b equals b. So we just have to let b equals 1, and then that means 2 times 1 equals 1, which means 2 equals 1 or 1 equals 2. Yep, that's a proof. Here is where the proof fails. So we start a equals b, we multiply both sides by a. That's all good, and then minus b squared on both sides. That's correct, no problem. But this step is still correct. But this step has a problem. The problem occurs here because a equals b, so a minus b is 0, so we can't divide both sides by 0. So this is where the proof fails. So we start with 1 equals 1. So that means 1 squared also equals 1 squared. 1 times 1 equals 1 times 1. It also equals, negative 1, negative 1. So that means 1 squared equals negative 1 squared. That means 1 equals negative 1. Just here. Like, square root is not the opposite of square. Like, that's what we have to bear in mind. Like, square root has 2 answers, in fact, if it is the opposite of square. For this proof, let's start off with negative 20 equals negative 20. So this means 16 minus 36 equals 25 minus 45. That's easy, right? The left hand side then becomes 4 squared minus 4 times 9. So this equals 5 squared minus 5 times 9. So now let's make the completing the square method. So now the left hand side can become 4 squared minus 2 times 4 times 9 over 2, and then let this plus 9 over 2 squared. So this equals 5 squared minus 2 times 5 times 9 over 2. And then we both add this, so add this 9 over 2 squared. So 4 minus 9 over 2 squared. So that equals 5 minus 9 over 2 squared. This implies 4 minus 9 over 2 equals 5 minus 9 over 2. Therefore, 4 equals 5. Therefore, 2 plus 2 equals 5. Okay, so this is a proof here. This time, the mistake is a bit more tricky to find than last time. So, all of these steps are right. Like, we can't spot a mistake. And all the way here, it's alright. But with this equation, like, this is not right. But wait a second. So, the squares both equal because 4 minus 9 over 2 is negative a half. 5 minus 9 over 2 is positive a half. So, you can do it by yourself. So, say both of them squared will give a quarter. So that all makes sense, right? But just bear in mind that the square is that there's no inverse to x squared. Like if x squared equals something, that there's two, that it's possible to have two numbers having the same square. So that means so these are the two numbers that have the same square, but that doesn't mean they're the same numbers. So this step is a mistake. D over dx. So this is a derivative of x squared. It equals 2x. But what I'm proving here is this equals x. How am I gonna do that? So x squared. So this equals x plus x plus x plus x plus x. X times, right? X times. With this rule, fx plus gx equals this plus, so this is a formula about derivative. So d over dx, the derivative of x plus x plus x plus x plus x, x times, yeah. So since the derivative of x is just 1, so that equals 1 plus 1 plus 1 dot 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 x times. So this just equals x. The floor here is here, so it's still x times. So the derivative of x, so we have the derivative of everything inside here, but the number of times is constant, which is not meant to be happening. So it's not meant to be x times. Derivative is a change, or the rate of change. So the rate of change as x changes, it doesn't only change inside here, but it also changes the number of times. So that means that this x shouldn't be x. This is not right. Suppose we have a circle. Well, I'm not good at drawing circles. I mean, it looks horrible, but okay. And we have a square outside it. So let's assume this is a, I mean, I'm pretty bad at drawing. Assume there are tangent lines, you know, and just assume it. Okay. Horribly drawing square and circle. Well, there's a unit circle with r equals 1. So the circumference of the circle is 2 pi r, right? So r is 1, so that is 2 pi. So let's find 2 pi. Okay, so now we have the square. The perimeter of the square is 8. Okay, so we pick a point on the circle and then draw a line that's perpendicular to the edge, like this. And then we will do it on like other sides too, and here. So, and yeah, we just keep on, we do that. Okay, so the shape outside the circle still has the same perimeter because we just basically folding this in. So let's continually doing this, like do that, keep on folding it. So the perimeter still stays the same, still stays 8, and this will just infinitely approach the circle. So the shape outside the circle is just approaching the circle infinitely. So when it's just infinite, it will be the circle. So that means you just have to calculate the, you know, the shape that's outside the circle that's infinitely approaching it, and that perimeter will still be 8. Why? Because like it is just folding a square inwards, which doesn't reduce its size. So now we have the 8, and then yeah, that's it. Well, so 2 pi is 8, so we have 2 pi equals 8. So that means pi equals 4. Proof. The flow of the proof is actually a concept of calculus, and this, like the way we're approaching the circle is actually not approaching it in terms of the perimeter, because it's not tangent lines or secant lines, and it's just those lines that doesn't approach. So in calculus, like if you approach something infinitely, like it has to actually approach it. Like the error gets smaller and smaller and smaller as you go. But this one, that's not the case. It's not getting smaller at all. It just looks like it's getting smaller, but for every single error, the infinitely many errors adding up together, so it will still be a reasonable amount of errors, not like actual calculus that infinite small errors, but as they get added up, they approach 0. There are infinitely many small errors, I mean. As they get added up, the error is still approaching 0. But here it doesn't approach 0. Every small scale is a reasonable error that will add up. So we just had to prove that any triangle is isosceles. Okay, let's start with drawing 3 lines. So find the midpoint of BC. Let's call it M. And there's a line going out that, and then draw the angle bisector of ABC, and then let them intersect at P. Okay, so now that both of the angles are same here, so we're just gonna label that. So we have PM, and then we draw a line PB and a line PC. So let's do the preparation. Yeah, and then let P align through P and perpendicular to AC, and that is E. And we do the same thing here, and let it be perpendicular at D. Okay. We have triangle APE equals triangle APD. So that's an angle side rule. So angle side rule, right angles. Okay, so these are saying, because they share a common line and angles, so we know that these are the same, these are congruent, and these are congruent because it's identical triangle. And we are also going to prove that triangle PMB equals triangle PMC. Well, this same because so this is perpendicular, and here's a common line. So PM is a common line, and BM equals CM because it's a midpoint. So we have this. So that is side angle side. Okay, they're the same. So that means these are the same. Okay, so due to the angle side rule, so we can have triangle BPD equals triangle CPE. So that means, so that is side angle with 90 degrees. Okay. So that means, so APE and APD are congruent, so these two are congruent. So we have AD equals AE. And then due to the fact that BPD and CPE are congruent, so that means BD equals CE. So we have BD equals CE. Well, we know that AB equals AD plus DB, or AD plus DB. Well, DB is the same as BD, they're the same. So that also equals AE plus CE. and that equals AC. So that means the triangle is isosceles. Okay, so I'll state the flaw of that proof. It's pretty subtle that the first time I saw it, I didn't realize, and after I see the reason is wrong, like, I got it. Okay, so we still have the M, so this is a midpoint. But if we just draw this, right, we just draw this intersection. But if we actually don't eyeball it and then actually see, I just turn around the paper to see, try to find the angle bisector. It actually, the intersection P is actually outside the triangle. It means outside the triangle. Here's P. Well, I mean, P. Yeah, P. Upside down P. So, well, even though all the equations are still correct, but that doesn't prove the triangle being isosceles. Yes, that's all the explanation. So this is really subtle, but if you get it, it's easy.